Для следующего доклада на сцену приглашается лауреат Нобелевской премии Уильям Мёрнер. Уильям Мёрнер, профессор из университета Стэнфорда, Соединенных Штатов Америки. В 1978 году в Корнельском университете защитил диссертацию по лазерной физике. Член Национальной академии наук Соединенных Штатов Америки, Американского химического общества и множества других научных сообществ. Область его интересов включает исследование физической химии и биофизики отдельных молекул. Под его руководством активно развиваются методы двух- и трехмерной визуализации сверхвысокого разрешения для решения задач клеточной биологии, таких как визуализация и определение структур белков в бактериях, изучение организации хроматина, исследование динамики регуляторных белков в органах движения микроорганизмов, изучение молекулярного движения отдельных молекул белков, ДНК и РНК в реальном времени, высокоточный анализ фотодинамики отдельных биомолекул в растворе, применение к исследованиям процесса фотосинтеза, белковых взаимодействий и транспорта. Профессор Мёрнер удостоен множества престижных научных наград, включая премию Ленгмюра в химической физике и премию Дебая в физической химии, а также Нобелевской премии по химии 2014 года за разработку флуоресцентной микроскопии высокого разрешения. Пожалуйста, профессор Мёрнер.
Well, I'd like to begin by thanking the organizers and my hosts for inviting me to come and speak to you today. It's a great honor and a privilege to help celebrate the 150th anniversary of Mendeleev's great, wonderful contribution, the periodic table. Of course, I was promised a microphone that I can walk around with, and it's sitting right here. So maybe we should set it up. Huh? And then I'll be able to walk around a little bit. Okay, maybe I can get this on. Oy, oy. This is really difficult. It's another challenge. As we're beginning, test 1, 2, 3. Okay, it's the best we can do. We have this wonderful pointer, but unfortunately you cannot see the pointer. And I'm disappointed about that because I was not allowed to use my own computer, and if I were using my own computer, you would see the pointer because it's built into the display. So I'm sorry about that. In any case, I'm going to tell you about this story of single molecules. But first, let's talk a little bit about this great day that we're celebrating and Mendeleev. You see, what was so exciting about Mendeleev to me is that he had this deep desire to understand the world by working to uncover patterns. And this has inspired all of us ever since in many ways. Actually, for me, learning quantum mechanics, which I had to do as a physical chemist, because that's what I am, a physical chemist, and the fact that it would, in a fundamental way, explains the patterns in the periodic table, that's a truly beautiful thing. And that's what led me to chemical physics eventually and physical chemistry. So now, the roadmap for my remarks here are going to be this story of physical chemistry and ultra-sensitive detection, and how industrial basic research led to these advances, having unexpected effects spanning physics, chemistry, engineering, and biology. So the early days of single molecule detection and spectroscopy will be the beginning. Then I'll talk about something called super resolution microscopy with single molecules, and then try to explain what can we learn if you can look at individual molecules. So that's the roadmap, and so let's get started back in the very early days. So thinking about resolution is part of the problem here today, and so to get all of this on in your mind. Resolution means the minimum distance in which you can distinguish two objects. And if you think of many, many orders of magnitude, you know that starting here at 100 microns on the far right, that's about the size of human hair, but going down by factors of 10, there are many, many interesting objects you'd like to understand. Cells, bacteria, and so forth, viruses, molecules, even single organic molecules, and atoms at 1 angstrom. So to observe these objects, you can use a lot of different techniques. You can use, on the left, these techniques, AFM, NMR, and electron microscopy, which have very high resolution, but they don't work in live cells, for example. And it's hard to see specific objects because you don't have a way to label individuals to distinguish them from the others. Light microscopy, on the other hand, is very non-invasive, and you can specifically label a biomolecule and then know which object you're observing. But the problem with using light is that the diffraction limit allows us to not see small structures beyond this boundary of about 200 to 300 nanometers, the wavelength divided by 2 times the numerical aperture of the microscope, which is about 1. That's the so-called diffraction limit. And so this whole idea of super resolution microscopy allows us to go beyond this barrier and obtain resolution down to 100 nanometers, 50 nanometers, 20 nanometers, and so on. So the breaking of the diffraction limit is the key thing that we'll learn about as my talk goes on. All right, so unfortunately, back in the 1980s, when we were thinking about detecting single molecules, Erwin Schrödinger, a great founder of quantum mechanics, said that we never experiment with just one electron or atom or molecule. And if we did, it would be as ridiculous as having a dinosaur in the zoo. So this is, of course, something that I didn't know about. It was published in 1952, but I didn't know about this when we did our first work, thank goodness. But the message for you today is, this is a few signposts that will appear up here. Beware when Nobel laureates say something cannot be done.